Hi, everyone. Thanks for coming to the MedPL seminar. So we're very happy to have Krish from Purdue University who's going to come and talk about his research a little bit. So thanks for coming.
Thanks for the kind introduction, John. Hi, everyone. Thanks for attending this virtual talk. Today, I'm going to talk about composable sound transformations of nested recursion and loops. This work is done in collaboration with my advisor, Milind Kulkarni. So lots of jargon in the title. Before getting into details of restructuring or scheduling transformations, let's see why do we care about them? Because they bring better performance through enhancing locality and exploiting parallelism of the program. Okay, so now let's see what kind of programs these restructuring transformations work well. One kind of program is the one with loopness. Loopness are prevalent in many applications such as image processing, PD solvers, machine learning, etc. Restructuring transformations such as loop tiling, loop fusion, and others for loopness have been researched for many years. Importantly, there are frameworks exist that unify those transformations. Another kind of programs is the one with recursion. Like loops, recursion also appears in many important applications such as simulation codes, data mining, graphics rendering. There are restructuring transformation developed for mix of recursion and loops in recent years, such as point blocking, traversal splicing, and others. But there's no unifying framework for those transformations. So in order to see the importance of a unifying approach and refresh our understanding of restructuring transformations, let's look at an example. Simple computation is nested under doubly nested loops. The piece of static code boxed in red can get executed multiple times dynamically. These different executions are known as dynamic instances. They are shown in small circles over here. So let's walk through an execution. For I is 0 and j is 0, a particular version of the computation gets executed, and I is 0 and j is 1, another version of that computation gets executed, and I is equal 0, j is 2, another version gets executed, and so on. So there are two important points to note here. One, this set of dynamic instances is known as the iteration space. Two, there exists a particular order of execution among these dynamic instances. So here it's shown with arrows. So now let's see how scheduling transformations looks like for loop. Let's take the previous example. Let's perform a code transformation in order to move the loop with index j out. This is known as loop interchange. So we can build the corresponding iteration spaces as we saw earlier. There is a one-to-one mapping between dynamic instances of input code and the transform one. The code transformation has changed the order of execution of dynamic instances. Originally, the instances were executed row by row, and after the transformation, they're executed column by column. This type of transformation that changes the order of execution of instances is known as scheduling transformation. So it's important that these scheduling transformations are composable. For example, take a doubly nested loop. Let's consider doing loop reversal. Say it breaks some dependencies, hence it's invalid. Let's try to perform loop interchange. Say it's also breaks some dependencies, so it's also invalid. But if we do loop reversal and loop interchange one after the other, that may result in a valid transformation. Hence, we need a way to reason about a sequence of transformations. In the world of loops, a framework such as polyhedral model can handle the composition of scheduling transformation. So now that we have a good idea about how scheduling transformation works for loops, to get our minds concentrated, let's look at an example where a mix of recursion and loops are being used. We are going to look at an algorithm called point correlation, widely used in data mining. There are endpoints in a k-dimension space. Here it's 2-dimension space. The goal is to count the number of points from these endpoints fall within the distance r from the query point p. The naive approach is to compare p with all endpoints that would quickly become an O(n) squared algorithm when there are n query points. The better approach is building a KD tree structure with n points in the dataset and traverse this tree with query point P and avoid computations with the points far away from P by pruning this traverse. So let's see how this is done. First, we build a KD tree with n points in the dataset. The tree is built by recursively partitioning the space where the points exist until we end up with one point in our partition. Root node A has all the points in it. We partition A into B and C, where each contains a half. Then we recursively partition those space until we end up with one point in the partitions, in each partition, corresponding to the leaf nodes. So consider node A. The space covered by node A intersects the circles around P. Hence, we further traverse B and C. The circle just intersects with the space covered by node B. Therefore, we don't have to traverse the subtree anymore. So we simply pruning this subspace away. The circle around P intersects with the subspace C. Hence, we further explore. It intersects H, and we go further. Now we have just one point left in the leaf node. Hence, directly compare, it falls within the circle, and we update the correlation. Again, the same case as before. Here, the circle intersects with the space, but direct comparison says that the data point is not within the range. So no update of correlation. So we can build a if we can build a well-balanced tree, then this approach of n query points is of n log n, which is better than n squared approach we saw earlier. How do we write the code for this algorithm? It's concise enough that I can fit the whole code in one slide. Of course, tree building part is a little complicated, so I left it out conveniently. For each point in a set of points, you traverse the tree repeatedly. In the recursive traversal, if the node is far away from the query point, you basically return. If it is a leaf node and the data point as a node falls within the range, then you update the correlation count. Otherwise, you traverse further recursively. So I would like you to notice a pattern in which a loop repeatedly calls a function. The function under the loop use calls to itself to recurse, and some computation is being performed in the innermost level of the nest of loop and recursion. We consider this kind of structure in code, which we call perfect nesting, and we will revisit this later in the presentation. So an interesting question we can ask is whether is it possible to build an iteration space for dynamic instances of a recursive code, as same as we saw earlier for the nested loops. Yes, we can. Let's look at a simplified example. Consider the loop that runs from 0 to n-1. For each iteration, we recursively traverse the tree and perform computation on each of its nodes. So let's walk through an example considering the small tree over here. In order to build the iteration space, we need to know the loop index I and which tree node n the computation is being performed. Dynamic instances are shown in small circles over here. When I is 0 and n is the root, a particular version of the computation is being performed. I is 0 and the node is left child of the root, a different version gets executed, and so on. Loops, we can build an iteration space here as well. So now let's see how scheduling transformation works for recursion. Consider the previous example. We perform a code transformation such that we traverse the tree once for each node, perform the whole loop of computation. This is known as a general interchange. So like Loopness, we can build corresponding iteration spaces. We can see a one-to-one correspondence between the instances and the change in the order of execution. Earlier, the instances were executed row by row, and the transform code, they get executed column by column. So in recent years, there has been significant amount of work done on developing scheduling transformations for mix of recursion and loops, such as point blocking, traversal splicing, and etc. These transformations work well in isolation, but there's no unifying framework. So why a unifying framework and composability of scheduling transformations are important? It's necessary to check the legality of complex transformations, which is composed of individual transformations that are not legal. Let's look at an example. The same code as we saw earlier with a little more complex dependencies. Let's take the post-order traversal and try to convert it into a pre-order traversal. The computation has dependencies with recursive calls, and these dependencies are broken here, hence it's invalid. Let's try to perform an interchange as we saw earlier. There are loop carry dependencies broken by this transformation, hence it's invalid too. But surprisingly, if you convert pre-order to post-order and then perform the interchange, it's a valid transformation. So we need a unifying framework to handle this kind of scenarios. The rest of the talk is about how did we build such a unifying approach called PolyRec. So there are 4 main pieces for PolyRec. PolyRec provides a representation of iteration space, a representation for transformation, a representation for dependencies in the program, and a procedure to check the soundness of the transformation. All 4 pieces work in unison to provide a framework of scheduling transformation for perfectly nested recursive program. So what's a perfectly nested recursive program or recursive functions? Once we transform all the loops in the program to tail recursive functions, if the computation happens only in the innermost recursive function, then it's a perfect nest of recursive functions. So the call graph of perfect nest recursive function takes a structure like this. Any function that have, any function can have any number of calls to itself. The computation happens only in the innermost recursive function. All right. So now let's take a look at the first piece of the puzzle. Let's look at an example. The same program as we saw earlier, but the loop has been converted into a tail recursion called foo. Let's take a specific instance where I is 1 and n is the right child of the left child of the root. Let's try to name this instance uniquely. First, let's label all the statements in the program. In order to produce the aforementioned instance, we must go through these statements. So when I hit a statement, I add the corresponding label to a running string. So I is 1, hence if we start with 0, then we must go through the recursive call R1. Then to traverse the tree, we should go through the call T1 to enter the function bar. In order to reach the node where the computation happened, we must go through the left recursive call and then the right recursive call. And finally, we end up at S1. This string is a unique name for the instance we consider. This is not a brand new representation. It has been used in Amiranov and Cohen's instance-wise reachability analysis. If you look at carefully, we are capturing the call stack information with this naming here. But we did something different. We split up the string in such a way that only the labels belongs to one function appear in a part. So for example, R1 and T1 belongs to foo appears in the first part of the string. We call these parts dimensions. The main challenge led us to choose such a representation is that iteration space is not affine. And it's difficult to map to an affine iteration space. All right, so let's summarize this representation. In order to name these instances, we need an alphabet. In addition to that, we impose an order on this alphabet. By imposing an order, we can lexicographically order the string. So for example, the string T1 S1 lexicographically precedes the string R1 T1 S1 for this given order. This lexicographical order is same as the execution order of the corresponding instances. For example, the instance I is 0 and n is root corresponds to the string t1 s1, and the instance I is equal 1 and n is root corresponds to the string r1 t1 s1, and the execution of the first instance, the execution of the first instance precedes the execution of the second instance here. Number of such strings are possibly infinite, but we can represent all of them succinctly with an automaton. An automaton that accepts the strings representing the instances in the iteration space. So we use multi-tape finite state automata to represent the iteration space. So let's move on to the next piece of the puzzle, representing transformations. As we saw earlier, scheduling transformation maps the input iteration space to a transform one. So an input iteration space can be represented with an automata, an input alphabet, and order on this input alphabet. Similarly, output iteration space also can be represented with output alphabet or a different alphabet and a different automata and output order on this automata, order on this alphabet, sorry. In order to map input instances to output instances, we need a function that maps strings generated by the input automata to the strings accepted by the output automata. So we can achieve this with the transducer. Transducers are composable, or at least we can produce an algorithm for a particular class. Hence, we can represent a sequence of transformation with a single composed transducer. So let me elaborate on that point. Say initially you want to, initially you have an iteration space. First, you want to perform chord motion and get a transformed iteration space. Then you perform interchange on that iteration space, and finally end up with a desired iteration space of yours. Now we can represent each of these individual transformations with different multi-tape transducers, and we can compose these transducers to produce a single transducer to represent this sequence of transformations. Now let's move on to the next piece, representing dependencies. What exactly a dependence here? So consider a pair of operations or computations, op1 and op2. Assume op1, op2 happens after op1 in the execution of the program.
I think the comment's a question.
Oh, hi, sorry.
Can you say why you need multi-tape automata?
Oh, it's a good question. Actually, the transformations that we consider, so for example, if you take interchange, multi-tape automata have, a good expressivity to express this transducer. I mean, like, finally what we are doing is mapping these strings to strings, right? This could be, we can also achieve this with like a push-down automata, but that makes the expressivity of the transformations much difficult. So like all four pieces should work together. So if we can represent the iteration space, but we couldn't easily represent the transformations that we consider, then it would be difficult to proceed further. So the main reason that we use multi-tape automata is expressivity of these transformations.
So the reason I'm confused is that it's known from push-down system model checking, and actually it goes back to Buchi at Purdue, although in the early 60s, so I don't think you knew him, that the stack configurations of a recursive program form a regular set. So it seems, I mean, you are going from a regular set to a regular set, and I don't understand why you need multiple tapes. What?
Yeah. So so for example, like let me pull up a different slide here. So say like if you want to perform interchange, this can be like a general interchange can be simply expressed with an automata, a multi-tape automata like this. So unless we don't have different tapes, then we might need some additional machinery to figure out to maintain this stack information. So we are just getting rid of that to express express the transformation in this format.
I'm not seeing that as an explanation, but go ahead. I don't think it's an important point. It's just you're using.
All right,
and that's fine.
Let me get back to that later. All right. All right, so consider the pair of operations or computations op1 and op2. Assume op2 happens after op1 in the execution of the program. So they access the memory by reading and writing to it. So if they access the same memory location and one of them is, or both of them are writes, then we say op2 depends on op1. We call them sink and source respectively. The order of execution must be preserved by any transformation for correctness. And this order relation between pairs of computation is known as the dependence. This way of defining dependence is commonly known as Bernstein's condition. So first, let's see how this is done for loopness. Consider the instance I is equal 0 and j is equal 0. It reads from the location A10. Consider the instance 10. It writes to the same location. Hence, there's a dependence exists between these pairs of instances. So we can see the similar pattern between other pairs of instances as well. So point to note here is that any scheduling transformation should preserve the execution order of the all dependent pairs of instances. So now let's see how this is done for a mix of recursion and loops. Consider the instance I is 0 and n is root. It reads from x1 of root. Consider the instance I is 1 and n is root, and it writes to the same location. Hence, there exists dependence between these pairs of instances. We can see a similar pattern exists between pairs of instances. So this we can see that the similar pattern exists between these pairs of instances shown here on the right. These pairs of source and sink instances, there exists a dependence from source to sink, and the execution order between this source and sink must be preserved by any valid transformation. So the interesting question is, how do we summarize this possibly infinite number of pairs? We can see the suffix part of all the source. Also, the suffix part of the all sink strings are the same. But for a given pair of source and sink, prefix is the same. So for example, here the prefix is R1 in the first tape, and R2L and R2R in the second tape, and so on. So what we can do is we can factor the prefix out by representing all possible prefixes as regular expressions. We can succinctly represent them, succinctly represent all these dependencies. We call this representation a witness tuple. So are these witness tuples completely different from dependence vectors in the loopness? Consider the code here and the iteration space over there. We can observe the dependence pattern between pairs of instances as we saw before. We can succinctly represent this pattern as a 1, 1 vector that can be placed anywhere in the iteration space. So let's see how witness tuple is analogous to the dependence vector. In witness tuple representation, a source suffix corresponds to the originating instance of the dependence vector. A sync suffix corresponds to the pointing instance of the dependence vector. And basically, prefix indicate the instances where we can place this dependence vector in the iteration space. In a way, witness tuple representation subsumes dependence vector representation for loops. So let's move on to the final piece, the soundness check. So the objective of the soundness check is determining whether a given transformation break any dependencies in the program. So this procedure must be sound. That means it should always tell us if a dependence is broken while reducing the false positives. The procedure must be able to work on composed transformations rather than individual ones. This procedure must be decidable. In other words, we should be able to give an algorithm to check whether any dependence is broken by the transformation that we consider. Okay, so for a given witness tuple, there could be infinitely many prefixes. Let's say we have a well-defined way to figure out whether a dependence is broken or not for a given prefix, which we will see next. For multi-step transducers that represent a composed transformation, we can find out the states that the strings in the pattern of prefix ends up. Hence, we can define a prefix transducer, which is structurally same as the transformation transducer that considers the states that I mentioned about or mentioned previously as the initial ones. All right. So now, say we have a composed transformation as a prefix transducer. In the input program, instances represented by sync suffix depends on the instances represented by the source suffix. Hence, instances I1 to IN, instances colored in purple, happens before instances J1 to JM that are colored in pink. So running these suffixes, or actually composing these suffixes with the prefix transducer and projecting them out will get us the corresponding suffix primes in the output program. If the dependencies are preserved, then the same ordering must be input program as well. That means on the side of the output program, all the instances in the purple must happen before all the instances in pink. Intuitively, this can be verified by checking the order between IN, the latest instance of the suffix prime, and J1, the earliest instances of the suffix prime in the output program. So we have produced a decidable algorithm to perform this check without explicitly finding IN and J1. So the details of the algorithms are a little more complex, so I'm leaving out here. If anybody interested in, I'm happy to chat with them. So we looked at a bunch of case studies. We have considered programs with severely dependent structure as the one used in point blocking and traversal splicing. We have performed these transformations as a composition of basic transformations in our general framework and achieve speedups over untransformed code. Note that in these cases, the individual basic transformations are safe. We have also considered programs that have little more complex dependent structure that are not used in point blocking or traversal splicing. So we were able to find a new composed transformation that has been presented in hasn't been presented in literature. So the individual basic transformations are unsafe here, but the composed transformation is safe, and the transformation also gives us speed up over the untransformed code. So we present a unified scheduling transformation framework for perfectly nested program, which represent iteration space, transformation, dependence, and an algorithm to check the soundness of compose transformations. So does the PolyRec cover all the possible scheduling transformation? Not really. Currently, we are looking at skewing. To understand better, we should see how skewing work for loops. Here on the right-hand side, I have shown the skewed code. It's easier to explain what's happening here with iteration spaces. On the left, iteration space for the original program is shown, and on the right, iteration space of the skewed program is shown. What happens here is that we have shifted each row by I. So 0th row shifted by 0, first row shifted by 1, and so on. So this transformation is always legal. But why do we perform such a transformation? To see, let's take a look at the dependencies in the program. Takes instance 0, 0, it writes to A01, and instance 1, 0, it reads from the same location, hence there exists a dependence. So we can see a similar pattern between other pairs of instances. If you see the columns, there are dependencies across the columns, and it's the same for rows. If you see the rows, there exist dependencies between the rows as well. So therefore, if you won't be able to parallelize along any of these loops. So once you perform or once you skew the loops, these dependencies are only along the columns. So remember, still we execute the instances row by row. So if you execute instances column by column, then we can easily execute them in parallel. So we saw this transformation before. It's basically loop interchange. So we can exploit parallelism by combining skewing and interchange together. All right, so we are exploring the question that can we use skewing for recursion? Yes, we can, but for a particular kind of recursion, linear recursion, a recursive function that has only one call to itself. The code here has the exact same structure as a doubly nested loop we saw before. This appears in the examples like a recursive mesh traversals. Skewing may benefit this kind of code, but why can't we use PolyRec's existing form to include skewing? The short answer is we can't use transducers to remove symbols from the steps. So this requires a significant extensions to the representation of iteration space and transformations. We can prove that given this extensions, we can still use the dependence representation and soundness check with minimal modifications. We call this extended framework UniRec since it resembles the unimodular framework for perfectly nested loops. All right, I would like to give a quick overview of the future work. We have restricted ourselves to perfectly nested recursive programs. We are planning to extend the framework to cover imperfectly nested recursion. Hence, we can have computation at any level of nested recursion, at any level of nested recursion. So this means like we are making the space of the program that we cover with this framework even more general. So we can use this to cover more interesting framework, more interesting transformation, such as fusing general recursion. So right now, we can represent iteration spaces for imperfectly nested recursion, but we still don't know how it affects the soundness checking algorithm, and also the way we represent dependencies. So I'm also interested in developing general dependence analysis. In PolyRec, we must provide the witness tuples manually by using an appropriate dependence analysis. But if we can neatly map the instances to reads and writes in the data structure that we operate on, then we can find the dependencies and produce witness tuples automatically. So this requires producing clever ways to take intersection of multi-tape transducers. So another area that I'm interested in is data layer transformation. There are multiple ways to linearize the recursive data structure that we consider, and a suitable linearization may enhance the locality of your program. So for example, if you're traversing the tree in post order, then having a post order linearization of the tree in memory gives you the best locality. Hence, you can see that the scheduling transformations and data layer transformations go hand in hand. So the choice of one influences the other. I would like to integrate ways of reasoning about data layer transformation to PolyRec. So that will be all for this presentation, and I'm happy to take any questions.
Thank you, Kirsch.
Thanks, Lawrence. So
yeah,
Tom,
I have many questions.
yes.
Okay. Thanks for coming and presenting it. So one thing is you started, or at one point you said, and I may have misunderstood, but you said something about you could not express the kinds of accesses that you needed in your recursive programs with the affine forms that had been used for loops. What happens if you take your generalized way of representing accesses and transformations and just back propagate them to loop programs? I mean, it's basically linear recursion.
Yeah.
And what do you get? Do you get anything interesting?
So the part of the latter part of the talk, I was talking about this UniRec, which integrates skewing. So actually, that kind of subsumes models like unimodular framework covers. That means basically we can, as you said, if you backpropagate, we can also we get the same results as we do in loop transformation frameworks. So
it sounded like you might actually get one thing that was more general. Because you had at the end for your recursive programs, you had this example of one where the individual transformations were themselves unsound, but their composition was sound. So was that also known for, or was the equivalent result previously known for loop transformation?
That is correct. So I can give you a concrete example. Usually in unimodular frameworks, they represent, I mean, in general, loop transformations are represented as matrices. So as I said, like you could find programs where all of these individual transformations are like individual transformation fails or like invalid, but still the composition of the transformation is a valid transformation. So one example is if you try to perform in a certain kind of program where you try to perform interchange and reversal together. And interchange also breaks some dependence, and reversal also breaks some dependencies. And if you try to compose them, they might the dependencies broken by one transformation may be corrected by the other transformation. So this is a non scenario in loop transformation frameworks.
So I have another question. In the context of program analysis, we have found linear recursion that's neither left linear nor right linear to be an interesting special case. So in language theoretic terms, left linear or right linear corresponds to regular languages. And linear, the general case, corresponds to languages like A to the I, B to the I, which is not regular, but it's not sort of fully context-free either.
Okay.
What you mentioned at the end was something about linear recursive programs. So you only had one recursive call.
Yes.
But the thing about a linear recursive program is that you have an action before the call and an action after the call. Is that an interesting case for you?
That is correct. So the action before the call and action after the call, as you said, can be considered as two different statements. our framework is still capable of reasoning about this kind of programs as well. I mean, like if you have dependencies between these statements, we are still able to check if any transformation is valid for that kind of programs. So as long as the statements exist in the innermost level of the recursive function, it doesn't matter how many statements you have. We can still reason about them.
Right. So in the program analysis context, it turns out that this was something known back in the late 60s, that the linear context-free languages are not that far away from the regular languages, in the sense that if you pair alphabet symbols, the A and the B, and you work with a paired alphabet symbol, then you have a regular language. You don't get A to the I, B to the I, you get A to the I stacked on top of B to the I. And if you read that as a tape that can be sort of unfolded, then you have the matching that you want. So is that an analogy with what you do? I mean, is there any analogy between that and what you do?
Yes, I think. Wait, I mean, I should be careful here. I'm not sure whether. I mean, like, I'm sure that this kind of, if you try to do any transformation for that kind of programs, we can handle them. But if you're asking me whether that is analogous to something that I have, that we have done here, I'm not sure about that. On top of my head, I don't have any analogies here. But any transformation to that kind of programs can be handled by our framework.
And are there actually interesting programs that do that? I mean, you used your example was a grid program, but I sort of don't think of a grid as being something which is the linear context free.
So some of this dynamic programming algorithms, where you, so for example, you have a grid and you recursively partition this grid and keep doing this. I mean, like people write those programs as bottom-up dynamic programming algorithms, and it's a little bit inconvenient, but you can express them as recursive programs. So in this kind of programs, you will do some computation before the call and some computation after the call. So that is one of the examples, one of the interesting examples that you might be, I mean, like that that falls into the case that you have mentioned about.
I guess the kind of thing I'm thinking about with like string to string correction, I sort of think of the grid as having 3 recursive calls, not 1 recursive call. So I'm a little.
I'm sorry, like
one dynamic programming algorithm on a 2x2 array is the string to string correction problem.
Oh, correct. Yes.
But there you end up saying that a given cell depends on the cell to the north, the cell to the northwest, and the cell to the west.
Yes.
That sort of naturally is expressed with 3 recursive calls, not 1 recursive call. So I'm.
Oh, you need 1 recursive call.
I'm so confused.
But this, okay, so I'm not sure whether we can represent, I mean, we have any programs with the which we can express as loops, but usually you have say like you have 1 recursive call, and if you have the statement above the recursive call, that corresponds to a forward running loop. And if you have the statement below the recursive call, then it's a like a backward running loop. But if you have both of them, actually what you're trying to do is like you're trying to express one whole computation that has both forward running loop and backward running loop together.
Okay. So I think we should take this offline. I'd be happy to talk with you at some point, not next week, but maybe in once June rolls around?
Sure, sure. I'm really happy to, because like I see like a lot of parallel between the work that you're doing in program analysis, and if you can make use of one of I mean like our work in any way, that would be really great.
Sure. Okay.
I have also a question. Like, so anything of what you do, I mean, can you do? There is this technique also called deforestation, where you remove intermediate data structures. So I didn't understand if what you do can also handle data structures, or is mostly about just individual computations.
Can you repeat that?
Like, I mean, what is the relation with deforestation, essentially?
Oh, okay. So actually, deforestation boils down to fusing general recursive calls. You have two recursive calls that traverse the tree, and if you fuse them, deforestation is most like you're fusing those recursive two different traversals on a tree. So as I said, in order to I mean, fully reason about this deforestation, we should represent imperfectly nested recursion. That means like you have multiple recursive calls, multiple recursions, and the statements are on like multiple levels. So right now we can represent imperfectly nested recursion. We can represent transformations on imperfectly nested recursion. But in this framework, the soundness checking algorithm and the dependence representation is not sophisticated enough to reason about deforestation. But we have done in a different work, we have done this fusing general recursive calls. So one of our examples is actually deforestation. Like we have reasoned about like deforestation passes, like take a functional program, I mean like compile for functional programs, and we have fused the passes in function that compile it together.
But you can only do that if everything operates with finite look ahead, right? So you can't.
That's correct. Yeah.
So, and I see. But how do you do it? I guess it has to be functional. You cannot do it if there is state.
I'm sorry.
You cannot do deforestation if there is state.
It's functional. Yeah.
So can one do a bit of both of the things you're doing? So imagine that there is a global parameter you're accumulating, and like deforestation usually just like, well, you take a tree, you turn it into another tree, and then you turn it into another tree, and you're removing the intermediate tree. But what if I'm trying to compute some quantity over these multiple passes? Like, I'm trying to do a name analysis or something, and
we can handle that.
We
can handle that. Yeah, as long as you write like a recursive function, like two general recursive function on the same tree, we can basically fuse them.
Okay. So I have another question. So is there any work on, so if I take a term rewrite of some kind over a program, I don't know if this is super related to what you're doing, but like, how can I prove that my rewrite is sound automatically? So let's say, I mean, can be something as simple as saying A plus B goes to B plus A. So that seems like something you can prove locally, but something like loop unrolling is also something that feels like you can locally prove automatically it is correct. But what is the limit essentially? Is that, I mean, people look at this.
So like when you fuse, say like you have like some arbitrary expression, and you try to do some rewrite and try to get you're trying to do a bunch of rewrites. So what you can think of these rewrites as traversals on ASTs, right? Like one way of thinking that is traversals on ASTs. So,
yeah, but that's hard. I don't want to prove that one is correct. I want to prove that there's a general algorithm.
Yes. So what we are like with fusing, what you can do is like if you have, I mean, like that is actually one of our examples, like traversing ASTs and performing some passes. If you have multiple passes one after the other, you're doing this passes one after the other, and if you fuse them, you can fuse them bunch of them together and have one single pass, we can say based on the properties of, or like based on the dependence that we had in the initial expression. I mean, if you can give us the dependence on each of these paths, what we can say is that if you fuse them, we can say whether it's doing the exact same thing as the rewrites doing before. So the rewrites that sequentially performing this, I mean, like if you're sequentially performing this rewrite, and I can fuse them together and give one rewrite, only thing that I can say is whether it's equivalent to the a sequential rewrite that you're doing.
You cannot do anything with respect to
you cannot say whether that a rewrite is actually correct. That actually depends on, I think the axioms of your rewrite, I guess.
Do you know if there is any work on that? Like, I know Alive can do stuff like this at the people level, but do you know if anybody has looked at more complex transformations?
So okay, so there are a bunch of works on general recursive fusion, but they are in various different scenarios. So our work, Grafter, which published in PLDI 19, try to perform fusion on any heterogeneous trees. There's a work called Minipass. I think it's from Martin Odesky's group. They were performing this. They were taking this. It was published in, I think, PLDA 18 or UPSLA 7. So they take all of these different passes in a compiler, and they try to fuse as much as possible passes together. But correctness-wise, I'm not sure whether anybody is doing a work on verifying the correctness of rewrites. Individual rewrites.
Mm-hmm.
But I think it's a very interesting question, because how do you know that individual term rewrite is correct, right? So maybe
no, but I'm assuming you're giving a formal operational semantics.
Yeah.
I think for certain things it's trivial, and that's what the Alive does, right? You have an axiomatized semantics of expressions, and then you just check that the SMT formula is unsatisfiable. But how to do it in general, it's a tricky. So I was mostly wondering if somebody has thought of a family of transformations that admits some equation of reading of some kind.
So there are I think you can separate your question into two pieces. It's whether your one what you're asking is, given a rewrite, whether this rewrite is doing the correct thing. So in our work, in our line of work, we define this by not breaking any dependencies in the program. So I think the question that you are asking is, how do I actually come up with those dependencies automatically for a given program? If we can come up with the dependencies for that given program based on, as you said, a very general dependence analysis based on the semantics of the program, and then we can definitely use, or we can modify our framework to use whether the dependencies, or check whether the dependencies are broken or not. So this, I think the question should be focused on finding the a right dependence analysis, coming up with a general dependence analysis for a program that you write in a particular language. So at least for if you try to come up with so let me go back to the slide here. So if you want to come up with a general dependence analysis for programs like this, we reason about instance-wise, the programs that does this instance-wise computation. then at least like I have a draft plan to do that. So so basically in our work, if you want to build up this general dependence analysis, you have to just tell me like what kind of data structures you have and a mapping between this iteration space and the data structures. Then it boils down to the question that can we take intersections of this intersection of the transducers, and the intersection of this transducer represent what are the instances that actually depends on one another. And then we have to, with that dependence, with that dependence relation, we should further move into the pipeline that we have. So yeah, there are like many interesting questions here.
Can I make a comment rather than a question? Okay. So a few years ago, I looked at a paper from Tjaar Courant. I think it was Uppsala a couple of years ago. And he had a very interesting scheme for naming points at program runtime so that they were uniquely identified. And then you have another person, Jingyu Zhang. I'm not quite sure what his first name is. So he does dynamic analysis, and he did a lot of work on, for purposes of debugging, having a notion of a dynamic, a point in the dynamic space. Yeah. It seems to be, and so I pointed out the connection between these two pieces of work from Purdue. They didn't know about each other.
Okay.
It seems to me you are yet a third person at Purdue who is working on essentially, or is attempting to do something very similar. Perhaps the three of you, or the three groups, ought to have some little seminar and exchange your techniques.
Yeah, I mean, like, yeah, I should talk to them, definitely. So one reason we might be like, which might be appear to be doing the same thing, but like the goals may be different. So for example, like
the goals are definitely different. One is debugging and comparing two programs for near equality. One, I can't remember what the other one was. It was creating some kind of functional intermediate form. And then you're doing parallelization and transformation to support parallelization. Yeah. So totally different things, but the sort of underlying base technique is unique names for something in a program's iteration space. So
that's correct, yeah. So yeah,
anyway.
I mean, like naming is the cornerstone of this work, I would say, yeah.
Right. Okay, thanks very much. And
thank you.
Maybe get in touch sometime in June. And
sure.
Okay.
It's really interesting work. Thank you that you're doing.
Okay, so thanks for doing a great talk. So I'll go ahead and